So our next speaker is Jan Oliver Ringert, and he's going to present a quantitative extension to assume guarantee synthesis.
Now it works. Okay, so hello. I'm going to talk about quantitative assumed guarantee synthesis, and this is joint work with Shaul, Orna, and Yaron. And the general setting is, again, reactive systems. So we have some system that reacts with its environment, like these robots. They get some inputs, and they produce some outputs, like where they are going. Then in reactive synthesis, we have given a specification. For example, go from A to B. And we ask the synthesizer to give us an implementation of the system that satisfies the specification, if one exists. So these specifications, they might have even multiple implementations. We see, for example, the one in the picture here. And the classic synthesis algorithms, they just look for correctness of the specification, but they usually don't guarantee anything about the quality of the implementation. And there are approaches to quantitative synthesis where we can formalize quality and then even try to optimize the quality of an implementation. So in our case, we will be looking at quantitative assumed guarantee synthesis. And for us, in this case, assumed guarantee synthesis means that we have some assumption that describes the environment behavior, and we have guarantees that describe what the system is supposed to do if the assumptions are satisfied. So there are some fragments of LTL which have efficient assumed guarantee synthesis. And what we want to do is we want to extend these assumed guarantee specifications with quantitative information and then maintain the efficiency of the existing solutions. So for this, we will specifically investigate two different ways to handle the Boolean implication, which we will then replace with a quantitative or different quantitative implications in our quantitative setting. First, we will look at a quantitative specification language. So LTL is just Boolean. The satisfaction value is true or false. And now there is LTLF, which extends LTL with a family of functions. And these functions then replace the Boolean operators. So this could be the maximum function, for example. And LTF is multi-valued. So the semantics of LTL, or the satisfaction value, given an LTLF specification, then the satisfaction value of a computation, this is an evaluation in the interval 0, 1. And we usually treat 0 as the Boolean false or the bad quality, and 1 is then true, the high quality, and we can have everything in between. So one example for an LTLF specification, this would be globally a request implies, and then we have an immediate grant and the weighted average with the grant in the next step. So this weighted average would mean that immediate grants after the request, if we always get immediate grants after the request, we have satisfaction value 2/3. And if we also get the grants in the next step, we would only have 1/3. If we get both, we have satisfaction value 1. And another example, so here we have something like negation. Now negation is a function, and we can define it as 1 minus the value of the that we negated. And conjunction, this could be defined as the minimum. So these are not fixed, but if you see with these interpretations, you would basically also get regular LTL by picking the right formulas. So now the synthesis problem is, usually when we have these reactive systems, we separate the atomic propositions into inputs and outputs. And then the solution or the systems that we model, they would be deterministic I/O transducers. This would be our implementations, like this one on the right side here. And now we also need to define what is the value of such a transducer for a given LTLF formula. So that's the satisfaction value of the transducer. And there we look at all the computations of the transducer pi, and then we take the minimal value on all the computations. So this is basically what does this implementation guarantee us in the worst case, the value that we still get from all the any computation. For realizability of an LTLF specification, we then asked what is the maximum threshold gamma such that the transducer exists that would obtain at least this satisfaction value gamma. And the synthesis would be for a specification, find or construct such a transducer that achieves at least this threshold. And the LTLF synthesis problem, which includes LTL, has a double exponential time complexity. So there is something, very nice fragment of LTL. It's generalized reactivity of rank 1 synthesis by Peterman, Prunilli, and Saar. And it's an efficient fragment for assumed guarantee synthesis. So the specifications, they have some safety part, but also fairness assumptions and fairness guarantees. This is what we will focus on. So these are down here on the slides. We have a set of assumptions, and we say if globally, finally, these propositions are satisfied, then it implies that we will have these fairness guarantees also satisfied. So this would be a generalized street 1 objective. And the synthesis time complexity here, this is the number of fairness assumptions times fairness guarantees times the state space squared, where the state space would be 2 to the number of inputs and outputs. And even though this might sound a little bit bad, there are efficient implementations, BDD-based, and quite a few tools have used Gr1 synthesis in practice. One example of a specification that we could, or a system that we could describe with Gr1 would be this. We have a workspace with 2 robot arms. They can spray in different colors. They color pieces in these colors, but they can only change the colors if it's supported by a human operator. So the human operator would be our environment. So we model when does the human support changes of the colored arms by the inputs, and the outputs would be the colors that the system produces. Then we have some assumptions. The operator always eventually supports the color change, and some guarantees that the colors can only change when it's supported. And we want the guarantees that we always eventually color in some color combinations. And this would be a specification from that we would want to synthesize an implementation of the robot. So in our synthesis tool, it would look like this: the inputs, the outputs, the color definitions, and the important thing down here, this would relate the fairness assumptions and guarantees by this implication. So globally, finally, change of the colors implies globally, finally, painting in different colors. This specification is realizable. But now if we want to move from the Boolean setting to the quantitative setting, what we need to do is we need to have some replacement for this implication. So we need some quantitative implication that also takes care of the values. And there are 2 that we are looking at. So one is the natural one, which we called the quantitative implication, where we simply have the Boolean implication, which is negation and disjunction, and then disjunction would be maximum and negation would be 1 minus. So we have the maximum of 1 minus the value of the satisfaction of the assumptions and the satisfaction of the guarantees. So if we get a bad satisfaction of the assumptions, then we have a high value that comes out, or we have a high value of the guarantees, then the synthesized value would also be high. Now there is something we try to do a little bit more. So you can also look at the ratio of the guarantee satisfaction and the assumption satisfaction. So basically what this would mean now, here you have this kind of the threshold 1 minus a. So if the assumptions are not so good, you don't care what the guarantees have to do anymore. But if we look at the ratio, we always have to kind of match the the value to get above some threshold. So high environment quality would also require high system quality, but lower environment quality would still require the system to match this. And this is already everything we need for the quantitative Gr1F fragment. We have quantitative propositional assertions. This would be the things that we want in assumptions or guarantees to always eventually happen. And this could be simply the atomic propositions mapped to 0, 1, or maximum over atomic propositions, and we can also scale them. So we can define any kind of functions for these quantitative propositional assertions. And the next thing is we need to combine the different assumptions and the different guarantees to group them with a quantitative conjunction. This would be this operator that maps many to one value of 0, 1. And then we have this quantitative implication that relates the assumptions and the guarantees. So the Gr1F fragment would have this nice structure where we have these conjunctions. We have the globally finally of the quantitative propositional assertions, and then our implication for the assumptions, and the same for the guarantees on this side. So for the realizability, we will then ask for the value that we can obtain to evaluate this function, the value that the I/O transducer could guarantee. An example for this paint robot, we have the first where we just choose the conjunction of the assumptions or something that corresponds to conjunction. This would be minimum. We use minimum as the conjunction over the assumptions, and we use average as the quantitative conjunction over the guarantees, and we use the disjunctive implication. Then what we get is maximum of 1 minus the minimum over the assumptions and the average of the guarantees. So we will soon see that for this case, it's not so very interesting because we get, again, realizability with value t equals 1. That's expected because it was already realizable. So we can get the highest average of this one would be if we satisfy all of them. And the minimum here, this means that we really trust that the human operator will always eventually serve the robot to support color changes. So if it fails in one of these assumptions, then the implementation has already won. It's done because we took the minimum, and the minimum of them, this would be then 0, and then we have the threshold 1 automatically. So now let's try to put the average here. Instead of saying minimum, we say, okay, we also look, we don't trust all of the assumptions that well. We take the average. And then the value, satisfaction value t that can be guaranteed is only a half. And the second example, if we take, now we want to look at the ratio. So we will look at sums as the conjunction. And then our ratio implication would divide the sum of the satisfied guarantees by the sum of the the quality of the satisfaction by the quality of the satisfaction of the assumptions. And here, in this case, it would be realizable for ratio 4/2, which is 2. So if we have 2 assumptions satisfied, we also have 4 guarantees to be satisfied. And if only one of them is satisfied, we can still paint in 2 colors because one of the arms changes the color. So we would also get 2/1, which is the same ratio. We will see that if we want to solve it efficiently, we have to approximate it, and then we only get 3 halves instead of 4 halves in our solution. So that's our main results. They say that Gr1F synthesis with disjunctive implication, we can reduce it to Boolean Gr1 synthesis with additional memory. This memory is basically this case. This was the number of assumptions plus the number of guarantees times we have a record for the achieved value in every assumption and guarantee. This is the variables that we add. And what we need for this reduction to work is that the number of fairness assumptions guarantees is fixed and that the quantitative conjunction is monotonic, because then we only have to remember the highest value that we currently achieved. And we will show that if we drop any of them, then we can no longer reduce it to the Boolean Gr1 synthesis. Gr1F for the ratio implication, we can only do efficiently for an approximation. And this would be finitary semantics, where we say that every value has to be matched with the ratio within some finite amount of time, but we don't have to give this bound. But there is some finite bound. And it reduces, we can reduce it again to a negated Boolean Gr1 game with even a little bit more memory. So the range here, this would be the values that the conjunction can evaluate to. And we have included the translation rules in the paper because we wanted to be also practical, and we did the reductions by hand for the example of the robot. And yeah, the bad results or lower bounds, this would be if we want to solve the corresponding games for Gr1F synthesis with disjunctive implication when it's non-monotonic, then instead of quadratic, it's NP-hard. And for solving it, if we don't have the fixed number of assumptions and guarantees, then it's co-NP-hard. And for the now the ratio implication, we showed that already solving it for a single assumption guarantee pair, it's as hard as it's interreducible with parity games. So that's why we decided to approximate it and then again reduce it to the Boolean Gr1. We ran it for this example. So in this example, we had these two inputs and we had the colors encoded. So this was 2 variables for the input, 16 system variables, and our reduction adds between 6 and 12 auxiliary variables. We see the values for the different combinations of the disjunctive implication and the ratio implication. So the most memory would be for the ratio implication, and the average on the assumptions and, well, average on the guarantees. It's in all these cases. But then we see that here this would be the largest blow-up of adding 12 variables, and then we see it's all in ranges of milliseconds. So this would be the highest values t that we can achieve. So yeah, this was very fast. We were happy. We decided to also do it for some larger examples. But then encoding it by hand is not so nice. So we decided for some, let's say, useful quantitative formula that we can reuse to compute the maximal, or to maximize the realizability of the, or maximal, yeah, to maximize the number of satisfied fairness guarantees. And we took unrealizable specifications because otherwise we would always get the ratio 1, which is the optimal. So we took unrealizable Gr1 specifications of AMBA, which had manually added reasons for unrealizability by Cimati, Roveri, Schupman, and Chaltsev. And what we used as the formula, we said, again, minimum over the assumptions, which means we trust that all the assumptions hold, and then average over the guarantees. So now if we maximize that, then we get how many of the guarantees can we really satisfy. What's the value that we could really satisfy? And we can see here, this is the maximum satisfaction value. We can sometimes even satisfy 7 out of 8, sometimes none, because they had safety problems, so the system would run into a deadlock. And we see here the time in milliseconds for the Boolean Gr1 on the original unrealizable spec. And here the time in milliseconds for our extended spec, where we reduced this quantitative Gr1F specification to the Boolean case. And we see that the ratios, well, of the running times, they go up kind of as expected, or even a little better than expected, because it's all symbolic implementations, BDD based. So the conclusion, we have introduced this quantitative assumed guarantee synthesis framework Gr1F, which is a subset of LTLF, and we have looked at 2 different implications. The disjunctive implication and the ratio implication, and we established upper and lower bounds by also reduction to the Boolean case of Gr1, which works in many cases when we have either the monotonic conjunctions or the finitary ratio objective. And the early experiments show that we can reduce these Gr1F specifications easily to existing Boolean Gr1 tools. Okay.
We have time for a few questions.
I will ask one. You started by motivating your work by looking at assumed guarantee things. And then you have these different implications, right? So there's been some work by, I think, Orna Koopfram on what I think was called rational synthesis, where you look at this as a two-player game, which made limited sense in a Boolean setting, but which would be really nice in this quantitative setting. Have you thought about that at all?
The rational synthesis, where you have strategies also for the environment players.
Yeah, so you could actually think of a large, you could think as implications, you could think of Nash equilibria or iterated dominance or whatever.
So to maximize for, okay. It sounds interesting. We have not, so it would be more fine-grained than the rational synthesis where you just have as good as, okay. Sounds interesting, yeah.
So it seems like all of the operators that you have sum and average weight all of your guarantees equally. Could there be a case that it might be useful to have weights say, I care more about this one than the other one?
Yeah, definitely. So what you can do is you can use any function that you can put there. So what you could do is you could still say, well, I want minimum of the first two, but then average of the remaining ones. So you can do this. And I think it's it depends how you trust your guarantees or how important they are for you. So it's really up to the specifier how to weight or how to put the quantitative values in the assumptions guarantees. But it's possible. Thanks.
Any more questions? Okay, then let's thank Jan again.